Today's lesson is on integer exponents. By the time you're done with this lesson, you should be able to apply the exponent rules, rewrite negative exponents as positive exponents. Good luck! Linear functions are those that grow by equal differences in equal intervals. In this unit, we will concentrate on exponential functions which grow by equal factors for equal intervals. To understand exponential functions, we first need to understand exponents. The following sequence shows powers of 3 by repeatedly multiplying by 3. Fill in the missing blanks. So grab your calculator and fill in the answers to each one of these boxes. If you didn't have a calculator, you could have continued with the pattern by multiplying by 3 and then going backwards, dividing by 3. So, this pattern can be duplicated for any base raised to any integer exponent. Because of this, we can define positive, negative, and zero exponents in terms of multiplying the number 1 repeatedly or dividing the number 1 repeatedly. So go ahead and take a minute and look at your integer exponent definitions. So most of you know number 1 very, very easily. Number 2, this one stumps you many times. Any base, and remember that base has to be greater than 0 and cannot equal 1, is going raised to the power of 0 is 1. And b to some negative exponent is 1 over b that many times. So when your exponent is positive, you're just multiplying by 1. And then multiplying b that many times is your exponent. If it's negative, it's 1 over that process. Exercise 2. Given the exponential function f of x equals 20 times 2 to the x, evaluate each of the following without using your calculator. F of 2. So, f of 2 equals 20 times 2, and x is this value in here, so to the 2. What do I do first? 20 times 2 or 2 to the second? Well, orders of operations says you do exponents first. So this is 20 times 4, which is 80. Next one, f of 0 is 20 times 2 to the 0. Well, we learned up here, anything to the 0 is 1. So 20 times 1 is 20. Do you see what's happening there? 20, 0, 20. F of negative 2. 20 times 2 to the negative 2. Well, according to this, b to the negative 2, so 2 to the negative 2 is 1 over 2 times 2, or 2 squared. So all I did was put it 1 over, and then I have a positive exponent. So 1 over 2 squared is 1/4, not 140. 1/4, so what's 20 times 1/4, or 1/4 of 20 is 5. You could use your calculator to verify that I did not make any crazy mistakes. So when x increases by 3, by what factor does y increase? And explain your answer. Well, let's look at this. If x increases by 3, so if I have 20 times 2 to the x, and then I increase x by 3. So say I have 20 times 2 to the first. That means I have 40. If I increase x by 3, that means I have 20 times 2 to the 4th. Well, 2 to the 4th is 2 times 2 is 4, times 2 is 8, times 2 is 16. So 20 times 16. Well, 2 times 16 is 32, so put the 0 on the end. So I went from 40 at 1 to 320 at 4. So I increased it by 3. So what did I do to this? Well, ignore the zeros. What do you do to 4 to make 32? Multiplied by 8. And notice I used my numbers to help me. So how would I explain? Well, If I'm increasing it by 3, that means I have 3 more powers of 2. So 2 to the third is 8. Hopefully that makes sense. There are many basic exponent properties or laws that are critically important and that can be investigated using integer exponent examples. 2 of the very important ones we will see next. Exercise 3. For each of the following, write the product as a single exponential expression. Write A and B as extended products first. So extended products. So what does 2 to the third mean? It means 2 3 times. Well, what does 2 to the fourth mean? 2 4 times. And when they're next to each other, they're being multiplied. So how many 2's do I have? 7 of them. So this equals 2 to the 7th. So in part B, 2, 2, 2, 2, 2, 2 for 2 to the 6th times 2, 2. So how many do I have? 8. So I have 8 2's. All right, so generically, what do you do when you're multiplying and you have like bases? First, you need like bases. If the bases are not alike, you cannot do this. You add the exponents. So this is 2 to the m plus n. So if we took 6 plus 2, we get 8. If we took 3 plus 4, we get 7. It's clear why the exponent law that you generalized in part C works for positive integer exponents. But does it also make sense within the context of our negative exponents? So part A, consider now the product of 2 to the third times 2 to the negative 1. Use your exponent law found in exercise 3C to write this as a single exponential expression. So 2 to the third times 2 to the negative 1 is 2 to the 3 plus negative 1, which is 2 to the 3 plus negative 1 is 2. Now, let's see if that really works. Evaluate, which means find the answer, 2 to the third times 2 to the negative 1 by rewriting 2 to the third and 2 to the negative 1 and then simplifying. So 2 to the third is 8. 2 to the negative 1 is 1 over 2 to the first power, or 2, so 1 half. What's 8 times 1 half, or 1 half of 8? 4. Oh, what's 2 squared? 4. Do your answers from A and B support the extension of the addition property of exponents to negative powers as well? Yes. Explain. Because you're just adding. We can add lots of different kinds of numbers. So because you are adding, it doesn't matter what form the exponent takes. So let's look at another property. Example 5. For each of the following, rewrite the exponential expression in the form of 3 to the x. Write A and B as extended products first if necessary. So if necessary. But let's look at this. So this tells me I need 3 of the 3 squareds. So I need 3 squared times 3 squared times 3 squared. So I have 3, 3, 3, 3, 3, 3. So how many 3's do I have? 6 of them. So I have 2 3 to the fourths. So I have 1, 2, 3, 4, 1, 2, 3, 4. I have 3 to the 8th. So what's my rule? How do I get 3 to the 6th for the first one and 3 to the 8th for the second one? So I get 3 to the mn because you multiply powers or exponents. Again, let's look at how it applies to negatives. Consider the expression 3 to the negative 2 raised to the 4th. Show this expression is equivalent to 3 to the negative 8th by first rewriting it as 3 to the negative 2 in fraction form. So, it tells us to write 3 to the negative 2 in fraction form. So, 3 to the negative 2 equals 1 over 3 to the 2. So, if I have this as 1 over 3 to the 2 4 times, that means I have 1 over 2 of them, 2 of them, 2 of them, and 2 of them. 3 to the 8th. Well, if that's on the bottom, doesn't that equal 3 to the negative 8 on top? Absolutely. You could have also, if it didn't say to rewrite it in fraction form, you could have also said I have 3 to the negative 2, 3 to the negative 2, 3 to the negative 2, 3 to the negative 2. I'm multiplying those. That's expanded form. So I have 3 to the negative 8 because I just add the exponents. So it does work. And if I do negative 2 times 4, I get negative 8. So that's expanding the product property rule. Cool. All right, so exercise 7. Now let's use what we know. Determine the integer value of n that satisfies the equation. Well, let's rewrite things. So 4 to the n. Well, 16 is 4 squared, correct? So, if the base is alike, then guess what? The exponents are equal. So n has to equal 2, right? Because 4 squared has to equal 4 squared. Makes sense. Ooh, this one's a hard one. 3 to the n equals 1 over 81. So 3 to the n equals, well, 81. 3 times 3 is 9, times 3 is 27, times 3 is 81. So this is 3 to the 4th. But it's on the bottom, so this becomes negative 4 to get it to the top. So n equals negative 4. Remember, if it's a fraction, that's a negative exponent. And the last one, 7 to the n equals 1. Well, 7 to what power is 1? 0. Gotta think about that one. That's the one that stumps everybody. So what does n equal? 0. So 7 to the 0 power equals 1. If you have any questions, please make sure you ask in class. Good luck.